of operating system, which is process synchronization and critical section problem. So let's get started. First we are going to understand what is processes, and we are going to see some terms related to it, and then we are going to jump into the critical section part. Let's understand what is program process. Program, a passive entity, is just like code resting on your hard drive. It is not getting loaded or executing. Right, now we have process, an active entity, a program loaded into memory and executing. Okay, now we have resource allocation, just from the name of it. For executing a process, we need some things like CPU time, memory space, input output access. Those are resource allocation. Now we have concurrency. Modern operating system runs multiple processes simultaneously, which means they often need to share resource, right? Now we have dangers of share resource. Sharing resource sounded efficient, but it is danger also. How? Let's understand the cooperating process, then we discuss the race condition. The cooperating process often need to share memory, variable, file or database. Okay, now we have threat race condition. I will use one example and I will use it for the whole video. Okay, and that example is, we have process A and we have process B and we have file 1. Okay, process A did some changes in file 1, process B did some changes in file 1. The thing is like they did it at the same time, so we don't know that what would be inside a file 1. So this whole thing we call data corruption. A final outcome becomes unpredictable and depends entirely on timing of execution. So for this whole phenomena we call it race condition. So we want this thing to not happen, so we jump into critical section part. A specific segment of code where process modifies shared resource. It's a specific part of code where process modifies shared resource, right? The conflict. If process A is inside critical section modifying data, process B cannot enter and must not enter, right? So race condition will not happen. What is our goal? To design synchronous protocol that processes can use to cooperate safely without crashing the system and corrupting data, right? Now we have rule number 1, mutual exclusion. What is it? The process is executing in critical section, no process can execute in theirs. Okay, what does that mean? If process A is in critical section making changes in file 1, then process B cannot enter in critical section, okay, and cannot make changes in file 1 also. And if process B is in the critical section, then process A cannot make changes in file 1. It's simple, right? So it kind of kills the right condition. What's the real word? An analogy, like a single occupancy restroom with a physical lock. Once someone is inside, everyone else must wait outside until the door is unlocked, right? Now we have progress. Prevent system stalls and deadlock. If critical section is completely empty, a process should be able to enter. A selection of the next processes cannot be postponed. Let's say we have process A and process B. Those processes gets executed, okay, and critical section is empty. So we have to execute the process C also, right? So it's just that thing, progress. You have to run process again and again, and it's not like one process is just staying there, not running at all. Okay, what's the rule? Only processes that are actively trying to enter in critical section can participate in deciding who goes next, right? Now we have bounded waiting. Prevent resource starvation. Every process must eventually gets its turn to execute. Okay, just by term starvation, that process must get execute. It's not like process A is waiting for 3 hours and process B get executed in just 30 minutes. No, there is a limit, right? The strict limit is like there must be a limit, a bound. If we're talking about we talked about the process A is actually waiting for 3 hours, so it should get executed. It's kind of starving to execute, right? how many times other processes are allowed to enter in the critical section after processes has made a request. Ensure fairness across all active processes, prioritizing older requests. What's the conclusion? The process synchronization is a vital for operating system. Yeah. Critical section isolate where shared resources are vulnerable to modification. First, we know that in modern OS we have to let process share resource because it is efficient. If they create a red condition, we have to follow all these three rules too. Okay, and process one process gets into critical section, and other one should wait till process A get executed, right? All those things. To prevent data corruption and race condition, any valid solution must guarantee mutual exclusion, progress, and bounded waiting. If these three are following in critical section or the process synchronization part, the race condition data corruption will never ever happen. Okay, thank you.